Hello, Didier Stevens here, analyst at Enviso, with a third video on decrypting Cobalt Strike traffic. Here in blog post 4 on our series of decrypting Cobalt Strike traffic, we handle obfuscated network traffic and also obfuscated process memory dumps. And here in this video I'm going to show you, just like you can follow it in the blog post, on how to deal with that obfuscation and do the decryption. So I'm using a tool 1768 to analyze a beacon, and here I'm first of all going to use a beacon, analyze a beacon that doesn't do any obfuscation at all. And the kind of obfuscation I'm talking about, traffic obfuscation, is done with malleable C2 data transforms. And if you look at the output of the tool, you can see here for post, here, and for get here, and also for headers, you can see malleable C2 instructions. So for the input, so for the data coming from the team server to the beacon, that is the input, we just have a print, so the data is not obfuscated here. And for the output, so data going from the beacon to the team server, we also have a print, not obfuscated. The session ID is just a parameter ID, and the metadata is base64 encoded and used as a cookie. So that is all default here, default behavior, without obfuscation. But you can have malleable C2 profiles that introduce obfuscation and that do transformations to obfuscate the traffic. And I have that in another sample here. If you now look here at the input transform, you can see that there are instructions like remove bytes from the end, remove bytes from the beginning, remove bytes from the beginning, do base64 URL encoding, then XORing with a random key. And also here for the output, XORing base64 URL. And this here is encoded in between those brackets here with this notation, these numbers here. For example, a 4 represents a print, a 15 is an XOR, a 1:1522 says remove 1522 bytes from end. Okay, so these are the instructions. And why does the beacon need to know about these transform instructions, these malleable C2 instructions? Well, if we look at the traffic here, so I captured the network traffic, I already filtered on HTTP, and let's follow this first GET request. You can see here you actually have something that looks like JavaScript. So it's not encrypted binary data, but it looks like JavaScript. And that is the transformation that is applied by the team server to obfuscate the traffic. The encrypted binary data is actually represented here in base64 and also XOR encoded. So you need to remove all that JavaScript data and then decode this with base64 and do an XOR decoding exactly as specified with the instructions here. And then you can obtain the pure encrypted binary data that you can then try to decrypt. And that is something you can automate. I mean, you can use the tools to do that. So we are going to first extract the encrypted data so that we can use that to find the keys in process memory. And remember, I said at the beginning, the process memory is also obfuscated, so that's something we're going to have to deal with. So I use tool here CS parse traffic pi. And so I don't know the key, just like we did in video 2. But now, instead of just doing capture like this, if I run this, I actually get a lot of data, and that's not the correct data. You actually need to tell parse traffic, CS parse traffic, to apply the transformations. So the thing to do is, from the output from the tool 1768, use that here with CS parse traffic and say I have transformations. Option T, transformations, and here you have the output transformation. I'm going to copy paste this and then semicolon to separate it from the input transformation, and here I copy the input transformation, so copy paste. So this is the actual transformation. I don't need a transformation. You can copy it, but that's not necessary. I don't need a transformation for the get header or the post header. I just need it here, in this case, for the input and the output. And I copy everything between the square brackets, and I separate it with a semicolon here. So let's run this. And now indeed we have here our decoded, encrypted, so deobfuscated, encrypted binary data. As you can see, the row length here of the data was more than 5,000 bytes, but actually we just end up with small sequence of bytes. So like I did in video 2, I copy this now, and then I use a tool CS extract key. This is a task, and I give it the process memory dump. And as you can see here, we don't get a quick result. It will take a bit of time, and nothing was found. Okay, and that is because the process memory is also obfuscated, and this is what they call in Cobalt strike terminology a sleep mask. A sleep mask is something that can be configured in the profile of a Cobalt strike beacon, and when a sleep mask is applied, the memory of the beacon will be XOR encoded while it is sleeping. So a beacon is sending a request to get instructions, and if there are instructions, it executes those instructions, and then it puts back the result, and in between it sleeps. So typically, for example, it can sleep for 60 seconds. So it is very likely, in a case like that, with a beacon that sleeps for 60 seconds long between each connection to the team server, it is very likely that you are going to take a process memory dump at the moment that it is sleeping, and then when such memory obfuscation is applied, then you will not have the key. The keys have been XOR encoded, and I have a tool for that to try to find that XOR key and do the decoding of a process memory dump. The tool is called CS Analyze process dump, and you just give it a process dump, and here if it found something and it wrote a segment to disk. So here in summary we are lucky. This is the XOR key. Now you don't need the XOR key, it's just printed here, but you don't need it because the memory segment that interests us has been decoded with this key and written to disk. So what I need to do now is again run, go back to the command here, this one, but instead on running it with the full process memory dump, I need to pass this the decoded one here like this, and as you can see now it found the keys, just like in the previous video, video 2. The difference here is that the traffic is obfuscated, but also the process memory is obfuscated, so we have to deal with that in both cases. So it is still searching if it finds other keys. And now searching for the row key. Okay, no other keys were found, and the row key was also not found, but we need the key. We have the key that we need here. So the HMAC key and the AES key. So I copy this, and then I go back to my csparse command, and instead of unknown I have the key now. Now it is important to give it the transformation, to keep the transformation. And as you can see here, again we have data jitter. Here is a timestamp. The traffic can be decoded, but there are no actual commands, just random data sent by the team server. So that yet is another level of obfuscation. If you wouldn't have given the malware C2 transformations here for the traffic, then the tool will not be able to properly decode the traffic, and you get HMAC signature errors.